Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all. Okay, this will be the last topic from my part, which is um, the last type of DC to DC converter, which is on buck boost converter. Okay, so we will begin the what we call the lecture by giving some introduction on buck boost, and then we go for the steady state analysis, where in this analysis we will what we call find the equation for the current for the passive component, okay, using steady state analysis. So we are going to use the equivalent circuit based on the switch operation to help us in deriving the equation in order to design a buck boost converter. Okay, so let us proceed. Okay, so first, okay, so what is the meaning of buck boost converter? Is that the difference between the from buck and boost. For buck boost, the output can be either higher or lower than the input voltage, which means that it has the two capability. It extract the advantage from buck and also from boost. So from this converter, the output can be higher or lower than the input voltage. Yeah. So if let's say that the output is higher than the input voltage, it will be acted similar to boost converter. And if the output voltage is lower than the input voltage, it will be acted similar to buck converter. Alright, so for buck boost converter, okay, the output voltage polarity, see, the output voltage polarity is opposite to the input voltage, which is it will give a negative output. Yeah, so sometimes it called as inverting regulator. Okay, so if let's say that we want to make it the output to be positive, so we need to insert what we call as a NOT gate or some inverting capability in order to make the output voltage to a positive value. Okay, so before we begin our analysis in steady state, there are a few assumptions that we need to consider. Okay, the first one is that we need to assume that the inductor current is always continuous, which means that in regardless the switch is on or off, the inductor current must always be continuous, must always be a positive value. Okay, the second assumption is that the average inductor voltage, so VL, will be equals to 0, and the average capacitor current will be equals to 0. Okay, the third assumption is all components are ideal, which means that there is no losses, so your input power will be equals to your output power. Okay, so this one is for assumption number 2, and this one for assumption number 3. Right, so this is how the circuit are being implemented for buck boost converter. There are two way to implement a buck boost converter. One is that we are going to use two switches, S1 and S2. So S1 and S2 will be complement to each other. Whenever S1 is on, S2 will be off, and the other way around. Yeah. Okay, and then for the second implementation, we use the what we call the switching the switches, as well as also the freewheeling diode. Okay, so from this circuit over here, we're going to produce two equivalent circuits based on the switch operation. So from these two equivalent circuits, we're going to generate the delta IL equation, and then we're able to relate these two the delta IL equation in order to get the final equation, which is the relationship between the duty cycle with the output and input voltages. Alright. Okay, so let us draw for the steady state analysis. Okay, for the first equivalent circuit first. Okay, so when your switch is on, right, so your diode here will become reverse bias. So we need to redraw back the circuit. So we have the input voltage, and then the switch here we add something like this, and then we have the inductor over here. Okay, and then we have the diode here. Okay, and also the capacitor and the load. Remember, yeah, the capacitor will always be connected in parallel with your load. You can see here, okay, the diode current, it will be this is the direction for the diode current. Okay, Vs, and then we have, okay, here is VL. Okay, I not here and IC here, V not here. Okay, so okay, based on the first operation, when your switch is on, the diode become reverse bias, where we replace the diode by an open circuit. Okay, oops, sorry, should be inverter, sorry for that. Should be inductor, yeah, and open circuit here. So since we assume in our analysis that the capacitor current is equals to 0, so we can omit that path of capacitor connected to your load, straight away to your load over here. Right, okay, this is the IS, IL, and I naught over here. Alright, so we can see from here, since your diode is being replaced by an open circuit, so which is it will be disconnected. Your load here will be disconnected from the circuit. It will be disconnected, yeah. So we redraw it back, it will become something like this. Your switch, and then your inductor over here. Okay, alright, so this is how the equivalent circuit when your switch is on and your diode become your diode become reverse bias. Okay, so from this circuit, first we begin the analysis from the voltage across your inductor. So VL, oops, okay, VL will be equals to, okay, since the only source that we have in this circuit is Vs, so VL will be equals to Vs, right? Okay, will be equals to L, so we define by in terms of current, di over dt, which is L, di over dt we replace by delta IL over delta T. Okay, and then we'll be able to get delta IL equation will be equals to, so Vs over L multiplied by our delta T over here. Okay, so your delta T here is referring to the duration of switch when it is turned on, which is it will be equals to dt. So Vs over L multiplied by dt. So you will get the first equation, delta IL equation, when your switch is on, which is it will be equals to Vs over L multiplied by dt. Okay, then we proceed to the second equivalent circuit when your switch is off, and when this is when your diode become forward bias. Okay, so we replace the switch by an open circuit here. Okay, and then your diode will become short circuit. Remember, this is how the diode flow. Okay. Alright. So from this, we can see that since your switch is being replaced by an open circuit, obviously your Vs over here will be disconnected from your load. So we redraw it back. Okay, the circuit here, so you will get a diode over here, and then your inductor. Okay, VL, IL, ID over here, and this is V0. Okay, this is your I0. Okay, so this is will be your equivalent circuit. When your switch is off, your diode will become forward bias. So from this circuit over here, okay, we need to okay, this is the how the current flow. Okay, we're referring to the inductor, because inductor will be the source of the energy. Okay, this is when the inductor will release the stored energy. Okay, and then in order to power up the load. Okay, so from this circuit over here, we need to produce the delta IL equation. Okay, we will start with the what we call VL, voltage across inductor. So VL will be equals to, okay, you can see here at this point over here, this is the direction of your inductor current. Meanwhile, the direction of your output current is the other way around. Okay, that is why you will get the negative V0 over here. Okay, so L di over dt. Okay, and then we replace by delta IL over delta T. Okay, so your delta IL will be equals to negative V0 over L multiplied by delta T. Okay, so delta IL when your switch is off will be equals to negative minus V0 over L multiplied by 1 minus T times T. So you get the second equation when your switch is off. Okay. Alright, so from we need to equate these two equations together, delta IL when your switch is on and delta IL when your switch is off. Okay. So delta IL on plus delta IL off. Okay, so previously we have a delta IL equation when your switch is on is Vs dt over L. So we substitute inside this equation. Okay, and then delta IL when your switch is off is minus V0 over L multiplied by 1 minus T times T. So once you have these two equations over here, we can cancel the similar terms and also try to simplify the equation in order to get the equation for your duty cycle. Okay, we take out the T over L here. Okay, VSD. Right, and then we have T over L, so we have the V0 minus V0 D, yeah, equals to 0. So you bring T over L to the other side, it will be multiplied by 0, so you get 0. Obviously, it will be cancelled out. So you will leave it with this VSD minus V0 minus V0 D equals to 0. Okay, so let's say we gather the one that have the D in the variable. So we have V SD minus V naught D. We bring the minus V naught to this side over here, it becomes positive V naught. So Vs minus V naught over D equals to V naught. Okay, so your D here will be equals to V naught over Vs minus V naught. So this is the equation of your duty cycle. D will be equals to V naught over Vs minus V naught. So since like I mentioned earlier, for the buck boost converter, the output voltage can be a negative value, so that we will put this epsilon over here in order to what we call to get to omit the negative sign. So regardless what is the sign, either positive or negative, in order for us to find the equation for duty cycle, so we need to omit the sign. Okay, alright, so from the one that I redraw it, just explain it just now, this is the equation. Okay, which is it's referred to the equivalent circuit when switch is on and off here, and I just solved the equation, prove the equation here. So this is the correct equation. So duty cycle D will be equals to V naught over Vs plus V naught. Alright, so we can see that the output voltage has a opposite polarity from the source voltage. Yeah. Okay, and then so the output voltage magnitude for the buck boost converter can be less or greater than the source or than the input. So it will depend on the duty ratio, the value of duty ratio for the switch. So if let's say that for buck boost converter, if let's say that you calculate the duty cycle and you get that your duty cycle is greater than 0.5, your buck boost converter will be acted similar to boost converter. Okay, so if let's say that you calculate your duty cycle and it is less than 0.5, so your buck boost converter will be acted like a buck converter. Okay, alright, so this is the what we call the boundary, whether the converter will be operated in as a buck or as a boost converter. Okay, so in this converter, we can see that it combine the features from the buck and also buck boost, from buck and boost converter. And we can see that from the two equivalent circuit, your source, your input voltage is never being connected directly to your load. Okay, so due to this reason over here, okay, some of the books, the reference book, it refer buck boost converter as an indirect converter. Okay, right, so these are the expected voltage and current waveform for buck boost converter. Okay, the first one we have the inductor current, second one is your source current, the third one is your voltage across inductor VL, and then the fourth one is your your output current, okay, I0, okay, in this case will be equals to your diode current, and finally you have the capacitor current. Okay, so these are the expected waveform that you should get whenever you do the OEL. Okay, try to zoom the waveform so that you'll be able to get similar, it might not be exactly the same, at least almost similar shape of the waveform. Yeah, okay, right, so we proceed the analysis in finding the rest of the parameter. Okay, so in order to find for your average inductor current IL, okay, we need to use the power equation. Yeah, okay, we know that from the analysis, one of the assumption is that we assume that the input power will be equals to your output power, which is this one over here. Okay, your V naught squared over R will be equals to Vs multiplied by Is. Okay, alright. So we can see here, okay, in this, okay, we proceed in order to find the average inductor current. Okay, it mentioned here the average source current or the average input current is related to the average inductor current by, okay, Is equals IL multiplied by D. Okay, how to get this relationship over here? You can refer to the previous slide, okay, which is you look at the inductor current and also the source current over here at this part only. Okay, at this part, right. So in order to find the relationship between these two current over here, okay, one of the way is that we can find the, in order for us to find the average quantity, we can find the area under the curve. So you can see here, this is the shape of a trapezium. So what is the formula in order to find the area for a trapezium? Is half multiplied by 2 parallel height multiplied by width, right? So we do this over here. Alright, so your IL will be equals to 1 over 2, okay, 2 parallel height, which is at this point here and this point over here. So you have IL min plus IL max, right? So multiply by our width is dt. Alright, so we need to integrate this. Okay, oh sorry, this will be Is. Okay, we need to integrate this over a period of time, which is 1 over t. So Is 1 over t, we integrate, okay, from 0 to t, and then this IL min plus IL max okay, and then over 2 multiplied by dt. Okay, so this IL min plus IL max over 2 is actually average value, right? So average value, which is will be equals to IL. Okay, and then once we integrate over 1 over t, so this t here will be cancelled out, and then it will leave us with IL multiplied by D. So this is how you get the relationship between your source current and your inductor current. Okay, let me write it to get a better. Okay, Is plus IL, this is how to find the average, right? This will be equals to your IL average. That's why we substitute here inside the equation. Okay, alright. So that is how the relationship between the source current with your inductor current. So we can substitute Is in from the power equation. Okay, with IL multiplied by D over here. So it's actually Is. Yeah. Okay. And then you can rearrange, take out the IL. So you will get IL. There are 3 equations you can use in order to find your IL. Okay, so this is the equation, right? And then for the maximum and minimum inductor current, okay, which is it will be equals to average inductor current plus delta IL over 2 for maximum current. For minimum current, we just change the sign from plus to minus. Okay, I'm using this equation over here to represent the IL. Yeah, okay, you can see that. Okay, and for delta IL, I'm using the delta IS 2 dt, Vs dt, which is this is referring of delta IL when your switch is on. Okay, and substitute inside IL equation. Alright. Okay, right. Okay, so once you get this equation, now you'll be able to find the equation for the passive component, which is the value of your inductor and your value of your capacitor. Okay, for the value of inductor, okay, remember there are two approach that you can use. Okay, first, let's say the first approach. Okay, I will recap it back. I already mentioned for the buck converter, and it is the same consideration that will be applied for all type of DC to DC converter in finding the value of L. Okay, we have two approach. The first approach, by using the we need to find what is our L min. Okay, how to find your L min is that we're going to set your IL min equation equals to 0. It will be the boundary between CCM and DCM. Okay, so IL min equation we have just now. Where is it? Okay, VST okay, then Vs dt over 2L. Okay, did I write it correctly? Okay, so we will equip this equation equals to 0. Alright, so we rearrange. We want to find what is our L over here, which is your L min from this equation will be equals to RT RT, yeah, oops. Okay, sorry for that. Okay, L min will be equals to RT 1 minus D to the power of 2 over 2. Alright, so this is the L min equation that you can get from the by setting the IL min equation equals to 0. Then in order to find the L that will ensure the converter to be operated in CCM. Okay, so we take the consideration 25% greater than L min. So 1.25 you multiply by L min. Okay, so you will get this equation over here. Okay, the second approach is that we're going to use delta IL equation. Okay, because in this, why is that we are using delta IL equation? Because in this equation it has L. Alright, so we need to find what is our L. Okay, so we set 40%. This is the what we call the common consideration that be used by the designer in order to find the value of L, which is delta IL is 40% of average inductor current. Okay, so once you find this equation over here, okay, so we substitute V delta IL is Vs dt over L. So from here you will get L Vs dt over delta IL. Okay, so you can use these two equation over here in order to find the value of your L. So it depends. Okay, okay, let's say that which equation that you're going to use, it depends on the question. So you need to look at the question, try to understand the question correctly. So if let's say that the question in the question it mentioned the words design. Okay, so if let's say in the question it mentioned the words design. Okay, design, remember design. Okay, so in designing you need to include both design approach. which is using the L min and using delta IL equation. Okay, if let's say that in the question it doesn't mention the word design, maybe it's just mentioned, okay, find or determine the value of L, and you need to look at the mark portion. If the mark is let's say 5 marks or maybe 6 marks, okay, you can use either one of the design approach, either the first approach or the second approach. But if let's say that the marks portion is quite big, okay, it's better to be safe, it's better for you to include both design approach using the L min equation and using the IL delta IL equation. Okay, right. So okay, so from here, okay, it mentioned in this form, in this point over here. So if let's say that we compare the buck converter with the buck boost converter with the same switching frequency and also the same R, okay, it is found out that the buck converter has the highest minimum value of inductor, which is the L min using buck is higher, okay, then compared to a buck, compared to boost and buck boost, so which is with the same switching frequency and the same R, okay, we will see that the value of the minimum inductor among these three converter, okay, buck will has the highest value of L min, while boost and buck boost will have a much lower L min. Okay, so in a way, so if let's say that you have the same parameter, okay, your frequency is the same, your R is the same, let's say that you need to use to choose among these three converter, what are the best converter that you should select. So with regards to the value of inductor, okay, it is better, it is suggested that you will use the lower value of L, because it will contribute to lower losses and it will not jeopardize your efficiency of the converter so much. So that's why if let's say that you need to select among these three converter, okay, with the same parameter, which one that you're going to select, so you need to select either boost or buck boost converter, okay, due to this reason over here. Okay, alright, okay, finally we're going to find the value for the capacitor, the equation for the capacitor. Okay, the equation for the capacitor for buck boost converter will be C will be equals to D over R multiplied by your output voltage ripple multiplied by your switching frequency. So this is how you're going to find the value for your capacitor. Okay, right, so we go for this example one over here. We need to design a buck boost converter that produce a negative 15 source, okay, from a 15 output, and the source is varied from 12 to 18 volt. Okay, the R here is 15 ohm and the switching frequency is 100 kilohertz. Okay, look at from this example, you can see that the output voltage ripple is not given, right? And there is no other information that can help you in finding your output voltage ripple. Let's say that if let's say that it gives you some waveform of your capacitor current, or maybe it gives you the waveform of your output current, so you from that waveform you'll be able to find your output voltage ripple. But here is only this statement over here. Alright, so since there is no other information that can help you in finding your output voltage ripple, you can assume what is the percentage of your output voltage ripple. Okay, like I mentioned in the previous slide, your output voltage ripple must be less than 5%. Okay, this is the recommended setting. Okay, so you can choose either 1%, 2%, 3%, 4%. Okay, as long as it less than 5% should be okay. Okay, right. So we will proceed, okay, in finding the answer for this example over here. So first step is that you need to find your duty cycle. Alright, find your duty cycle. Here V0 will be equals to V0 over Vs plus V0. Okay, so since we have two Vs, so you expect to have two duty cycle. Okay, which is, let's say, D1 over here. So 15, 12 plus 15. So you will get 0.56. Okay, D2. Okay, when your input voltage equals to 18, 15, 18 plus 15. So you will get 0.455. So I round up a bit. It could to 0.46. Okay, once you find these two, okay, you can proceed. Alright, we need to find our IL. Okay, since you have two duty cycle, obviously you have two IL. So IL1, let's say we are referring to duty cycle number 1, yeah. Okay, 1 minus so you will get 2.314 M. Okay, and then for IL2, this is referring to duty cycle number 2, which is 0.46, and also referring to Vs equals to 18, yeah. Okay. Okay, you will get this one here is 1.893 M. Okay, right. So we already find, once you already know your average inductor current, okay, we can find the rest of the parameter. Okay, so I will show using the two approach in finding the value of L.